So welcome everyone to the last session of our robotics fundamental or robotics mechanics fundamentals. In this session I'll talk about now the more, I would say, complex topic, which is the inverse kinematics of manipulators. Now, as I said before, basically when it comes to forward kinematics, we have the control parameters or the joint parameters as an input, and the output is actually the Cartesian space or the coordinate system or the position, for example, of a point. And the inverse kinematic is the reverse of that, which means that we want to basically predict or calculate or estimate the joint parameters as a function of the coordinate system. And this basically, as I said in the beginning, this is what is actually the practical case of or the practical model. Because in practice we have the coordinate system, or let's say we have the coordinate of the end effector, and I would say I want to move this coordinate from this position to this position, and this movement basically, of course, needs some changes in the input parameters, so in the joint parameters. So I want to predict these joint parameters, and this is basically the inverse kinematic. So forward kinematics, the angles or the joint variables. I'm not saying because they are not only angles, as we have seen, there are also some prismatics, which basically displacement parameters. So we have either displacement or rotational, for example. In this case they are input, and we have the output is the coordinate system of the end effector, and here is the reverse case. They are represented in this way. So this is basically the inverse kinematic, which is a function or the inverse function of the forward kinematic. This is basically the forward kinematic function, which is where the coordinate system is a function of the control parameters, and here is the parameters are basically the inverse function of the coordinate systems. Now, there are different ways to inverse this problem. So we need to start first always with the forward kinematic model, and then we can inverse this model to get the inverse kinematics. Now there are different ways to do the inverse kinematics. We will see them today. One of them, or the first one actually, and the most popular one, is the algebraic method. So the key here is to express analytically the joint angles as a function of the end effector. This is our target. What we need to achieve, if you remember, in the displacement analysis or in the velocity analysis or the acceleration analysis in the first the 3 sessions, we talked about algebraic analytical methods to analyze velocity and position and so on, and one of the ways is the algebraic, and basically in this way we always needed some nonlinear equations. We need to find these equations, and we need to find equations where the number of nonlinear equations equal to the number of degrees of freedom or more. So this basically, if we can achieve that, then we can solve these equations and we can get this variable. So the degree of freedom is equal to the number of joint or number of basically variables that we are looking for. So each joint angle can be solved as a system or by the system of the equations. Now, given an n degree of freedom, then for each joint we have the following equation. Now, what we see here is, which is basically the algebraic way of doing inverse kinematic, is we see here now the transformation matrices. First, this is representing transformation matrices. This is from 0 to n. This is from j to j minus plus 1, and this is basically from I to I minus 1 minus, which is basically here the inverse of this matrix. Now what we are seeing there is that if this basically is here, but actually this was on the right side, and what happened is that you bring this to the left side, as we'll see later. You multiply it by the total transformation matrix. This basically operation is one of the steps that you would need to do to find the system of equations. So if it's still confusing to you, don't worry, now it will become more clear. So let's say we have this system, which we actually have seen in the previous example of the forward kinematics. And I said these are called the rotational components, and this is the positional components. These are the set of transformation matrices from 0 to 6, where we have 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, and so on. And we are doing these multiplications until we have from 0 to 6 transformation matrix. Now, to find the inverse kinematic solution for the first joint as a function of the known elements of t base in the vector, which is 0, 6, basically what we need to do is first take the first term, which is the first transformation, t01. We multiply both sides of this basically model with the inverse of that transformation matrix. What is the goal here? The goal is that what I want to do first is actually to get theta 1 or q1 as a function of everything else. So I want to have set equations where in each equation I would need basically to have one target variable, and this basically we start with theta 1. So what we are doing is multiplying both sides of this equation with the inverse of t01. So on the right side, t01 would vanish because of the inverse multiplication. On the left side, it will stay there, and on the left side, we will see the q1 or theta 1, which will be as a function with which we can get the equations where q1 is on the left side and equal to other parameters on the right side. So this is what I'm saying there. So if I basically doing that, so the multiplication will get their identity matrix, so which means that this would vanish, these two terms, and we would have on the right side t1 2, 2 3, 3 4, 4 5, and 5 6. On the left side it will stay, but we need to multiply it, or we need to get the inverse first, then multiply it with the total transformation matrix. Now, to find more equations, and we will see now example of what these equations are and how we can find them, but to find equations for other parameters, because here you would find basically some equations that basically if the matrix is basically here 4 by 4, so you would, for example, on the left side you would have so 16 equations. In general, you would have 16 equations where, for example, this one is equal to the corresponding part on the right, this one equal to the corresponding one on the right, and so on. So you would have 16 equations. Now, so now we need to, for example, here we have, let's say we have here 6 variables. And if I multiply only, or if I do only one step of our algorithm, which is basically multiplying the inverse of the first term with both sides, it would not be enough to find this set of equations, because we need to find 6 set of equations basically, that's at least six equations where basically I can have all this, where basically all these are unknown and everything else is known. So these 6 variables are unknown, and everything else is known. So this definitely will not be enough. So what you need to do is to continue, like you would need to multiply now both sides with 0 1 1 2 inverse, then 0 1 1 2 2 3 inverse. You need to continue until you find the total number of equations that you are looking for. You could find them at this step, you could find them at this step, so it's not necessarily that you need to do all together. Now let's see an example just to give a clear picture. This is a very simple robot arm which has 2 links only. It has 2 degrees of freedom. We have here theta 1 and theta 2. This is the DH parameter, and these are the transformation matrices, which is 0 1 1 2 2 3. And this is a total transformation matrix, which is 0 3. So the algorithm says first let's multiply both sides with 0 1, basically inverse, and the target is now to look for theta 1, because it's our first variable that should exist, or actually this is the control variable of 0 1, right? So we would end up with these 2 basically sides of an equation, and this is basically how they are presented. So we are multiplying this with our transformation matrix, and this would be on the right side. So we would have set of equations, and what I want to find is sum of equations, so a set of equations where, let's say, if theta 1 is there, that's good. But if also can find other thetas, for example, if I can find two equations like we see here, where theta 1 and theta 2 are the only unknown in these two equations, then I can solve it, right? So this is what basically has been done there. What you see that they derived these two equations where actually, or they detected these two equations by just multiplying these two. And they found that actually in these two equations, everything is known except theta 1, theta 2. So we don't have theta 3, theta 4 here, and we have only two equations, and everything is known, which means I can now actually take these two equations, I can solve them. So we have two equations with two variables, or with two unknowns. I can solve them, and I can get theta 1 and theta 2, the arctan, for example, of other parameters. So this is basically how it is done. It's very simple in this case, and we have theta 1 and theta 2, and it was enough, actually the first phase was enough to find two equations where theta 1 and theta 2 are unknown and everything else is known, and we can derive or we can get to the solutions. Now this is the more complicated case, of course, which is the robot arm that we have seen to stand for robot arm. Now we have here transformations. Basically we have 6 transformation matrices from 0 to 1, 1 to 2 until 5 to 6. And we have, this is basically the rotational transformations. This is basically the positional transformation, and this is how it's represented. It's called also the axis transformation, and this is the origin transformation. This is basically, as I said, more like linear displacement, and here more like rotational. And what is happening here is they are applying the algorithm. So first multiply the both sides with 0, 1, 1, 2. Sorry. Actually here what happened is that they directly started with 0, 1, 1, 2 because they tried 0, 1. It didn't work out. It was not enough to find the set of equations. And if you do 0, 1, 1, 2, you can actually get 3 equations that you can see here, which include 3 variables, 3 unknowns. They are theta 1, theta 2, and d3. Remember, d3 here is a variable because d3 represent this prism. And what they found the 3 variables with 3 equations. Everything else is known except the 3 variables. We could solve them to find these variables. Now here basically the last 3 variables may be found using other element of each side. So what they are saying here is that actually I still can look here without going deeper, without adding more multiplication. After considering that I have solved now for theta 1, theta 2, theta 3, I can now look for other equations where, for example, here as you see theta 5 on the right side, the cosine theta 5 on the right side, and on the left side we have basically a terms basically where only theta 2 and theta 1 are unknown, but theta 2 and theta 1 are solved here. So I can use this to get theta 5. So we have now theta 1, theta 2, d3, theta 5. We, for example, still need theta 4 and theta 6. And basically this is what is happening. It does not guarantee solution for general structure, and even if it exists, it's complicated for increasing degree of freedom. So it's basically the drawbacks of algebraic method. What is happening is that we can continue doing basically now the multiplication, looking for solution for theta 4 and theta 6. Okay, now actually if I look here directly, if you're with me, basically we can actually use these two now terms to solve it for theta 4, because now 1 is known here, 5 is solved, and what is remaining is theta 4. So we can take it also, we can get theta 4. And theta 6 is again can be found from here. So in general, basically we can find theta 4, 5, and 6 using only the first or the second actually multiplication, which is 0, 1, 1, 2. Now there is an issue of or there are drawbacks of the algebraic methods. The drawback is, like always, when you solve equations, you can get many solutions, not all unique solutions. And this actually could cause a problem if you don't have some kind of constraints on your manipulator, or if you don't know the degree or actually the working space, what is called, of the limited working space of the robot arm. For example, here we have the first two, theta 1 and theta 2, where we have basically two equations. And here, which is a 2D planar, it's basically this equation here, this example, sorry. And what is happening here is that we are solving these two equations and we get 4 solutions, or 4 sets of solutions. It's either basically theta 1 is equal to 30 degree and theta 2 is 60 degree, or theta 1 is 30 degree and theta 2 minus 60.